So here's an example problem on currents in parallel wires and the overall magnetic field that they produce, as well as what sort of force of attraction or repulsion do they exert on one another. So you can see two wires are shown. The one on the left carries a current of 6 amps into the page, and the wire on the right carries a current also of 6 amps but pointing out of the page. The two wires are separated by a distance of 60 centimeters. And the first question we have to solve is, what's the overall magnetic field due to the two wires combined at the midpoint? So if we draw a line connecting the two and identify the midpoint, and that midpoint is located at a distance of 30 centimeters from either of the wires. Okay, the second question is, what's the net magnetic field, not at the midpoint, but up here at point P? So I'll make up a value. I have in mind that point P is at a distance of 50 centimeters from either of these wires. So in other words, point P lies directly above point X, right? It's in line with the midpoint. And then the last question, part C, what's the force per unit length that wire number 1 exerts on wire number 2? And does that represent a force of attraction or a force of repulsion? So let's just take this one step at a time. Do part A first. We don't need all of this notation. So we're just trying to find the magnetic field at this point right here. So we're going to use the principle of superposition, meaning we'll find what's the magnetic field due to the current in wire number 1, and for a moment then we'll ignore that wire number 2 is even there. Okay? And then we'll find what's the magnetic field due to wire number 1 while we ignore, what's the magnetic field due to wire number 2 if we were to ignore that wire 1 is even there, and then we'll take whatever those two magnetic fields are and add them together. So first of all, we got to figure the direction of the magnetic field. So let's take a moment and ignore wire number 2 and just picture the magnetic field lines associated with the current in wire number 1. So based on the right-hand rule, point your thumb into the page in the region of wire number 1, and then let your fingers curl around in a circle, and I think you'll see that your fingers are wrapping around in a clockwise circle to represent the magnetic field lines that exist around wire number 1. And so if I extend this circle to the point where it meets the point in question, then tangent to that circular path right at this location is some magnetic field that would point down. So I'm going to call that B subscript number 1. Okay, now for a moment, let's ignore wire number 1. So the magnetic field lines for the current in wire number 2, the direction can be found again using the right-hand rule. So point your thumb out of the page and your fingers should wrap around in circles. So there's a magnetic field line that wraps around like that, and like that, and like this. Okay, and so if we extend this, it wraps around and it also points downwards. So there's B number 2. And so because of the symmetry of this problem, it's the same current in each case, it's the same distance to the midpoint in each case, then the value of B1 and the value of B2 are equal, and so we can just call it really 2 times B naught. So let's figure out what the value of B naught is, and then we'll double it to get our answer to part A. So we can just use the formula that we found previously in this unit that says at any distance from a long straight wire, magnetic field is equal to mu naught times I divided by 2 pi times R. Now something we haven't indicated from this equation, it simplifies a little bit, so there's a name for mu naught. That's a fundamental constant in our universe known as the permeability of free space. Its value is 4 pi times 10 to the negative 7th in units of Tesla meters per amp. So if we're going to multiply that times some amount of current and then divide that by 2 pi times some value of radius, we might as well just cancel out the pi and say 4 divided by 2 is 2. So another form of this equation says the magnetic field at any distance from a long straight wire is 2 times 10 to the negative 7th Tesla meters per amp times the ratio of current divided by distance. So there's no name to this fundamental constant, but it's what you get when you divide the fundamental constant by a value of 2 pi. So if we go with that and replace I with 6 amps and replace R with 0.3 meter, 30 centimeters, 0.3 meter. Meters cancel meters, amps cancel amps, we'll be left with Tesla. 6 divided by 0.3 is the same as 60 divided by 3, which will give you 20. So we've got 2 times 10 to the negative 7th Teslas times 20. So we get B naught is equal to 40 times 10 to the negative 7th Tesla. And because we have double that amount, because the superposition principle says the effect of both currents add together in this case, then the net magnetic field at the midpoint is equal to 80 times 10 to the negative 7th Tesla. Now it might be worth noting, if we had suggested that current number 2 is 6 amps going into the page, then can you argue that the net magnetic field at the midpoint would be 0? I'll leave it up to you to think about that. Okay, let's go on and do part 2. So we've got the same picture, but now we're asked to find the magnetic field here at this point P that lies above the midpoint that joins the two wires. So if this distance is given as 50 centimeter and this distance is given as 30 centimeter, then this must be 40 centimeters just based on the Pythagorean theorem. We have a right triangle. So again, we'll take the approach using the superposition principle and ignore what's going on with wire number 2 and just take it one step at a time. So for wire number 1, there's a current that produces a magnetic field that goes in clockwise circles. Point your thumb in the direction of this current. Your fingers curl around in clockwise circles. So if we make a clockwise circle that passes through point P, then that represents a part of the total magnetic field line that wraps around that wire. But it's good enough just to show a portion of that magnetic field, because all we're really looking for is what's the value of that magnetic field right at point P. So we can draw a line tangent to that circular path and call that B subscript 1. So in the same manner, you can point your thumb out of the page and imagine a circular magnetic field line with this wire at its center that goes around in counterclockwise circle and passes through point P. So that's a circle that goes around like this. So we draw in a line tangent to that circular path at this point. And so we have a bit of a vector diagram here. We have magnetic field number 1 due to the 6 amp current that's flowing into the page, and we've got magnetic field number 2 due to the 6 amp current that's flowing out of the page, and we need to find the resultant of those two magnetic fields based on the superposition principle. So it looks like some components are going to cancel each other out, right? When you have two vectors that point in these two directions, you could break those vectors into components, and there's a component to the right that we can call B1 subscript x, and then there's a component to the left from magnetic field number 2 we'll call B2x, and because of the symmetry of this problem, we know those are going to be equal, and so there is no overall magnetic field along the x-axis. All we really have are two components that both point downward. We have B2y, which adds with B number 1y, and so we could call this 2 B naught subscript y, which would be 2 B naught sine theta, if only we knew the value of this theta. So let's take a peek at our diagram and see if we can figure that out. Maybe it's best if we draw this again. So let's focus on the magnetic field that surrounds wire number 1 and pay attention to this right triangle here. Oh, by the way, if 50 centimeters is the radius of this circle, then the distance from here over to here is also 50 centimeters, right? Okay. So we have a right triangle with a hypotenuse of 50, an adjacent side of 30 centimeters, and an opposite side of 40. And so I believe that this works out to be a 53-degree angle. And then this represents the clockwise circular magnetic field lines that circulate around wire number 1. And then we've got this magnetic field, which represents this B1 pointing tangent to that circular path. So the angle between any radius and any tangent line is an angle of 90 degrees. And by the way, if this is 53 degrees and this is a right triangle, then this angle over here is 37 degrees. But if the angle between this line and this line is 90, then this is 53. So if I show the x-axis and the y-axis, then this angle right here is back to that 37-degree angle. So we found the value of theta we were looking for. It's 37 degrees. So our overall magnetic field at point P, which is equal to 2 times the vertical component of either one of the magnetic fields, B1 or B2, multiplied by sine of theta. This comes out to 2 times mu naught I over 2 pi r, right? 2 V naught, well, I guess by putting in sine theta, I'm stating it as the y component. So B naught is mu naught I over 2 pi r, where r in this case is now, what, 50 centimeters? I is still 6 amps. And then sine of 37 degrees. In a 37-degree angle, that's the same as the angle in a 3, 4, 5 right triangle of this arrangement, right? That would be 37. So sine is opposite over hypotenuse, so we could replace sine of 37 with 3/5. Okay. So do the number crunching here. Mu naught divided by 2 pi is the same thing as 2 times 10 to the negative 7th. So we've got 2. We've got mu naught over 2 pi, which gives us 2 times 10 to the negative 7th. Then we've got 6 amps times 6. And then we have to divide by r. 50 centimeters is 0.5 meter. And then we need to multiply all of this times 3/5. So if you grab a calculator and work that out, you should get 28.8 times 10 to the negative 7th Tesla. All right. So the last part of this problem, part C, do these wires attract or repel each other? Okay. Well, now that we've seen the question, let's clear a little space. Let's use the superposition principle and take it one step at a time. Say, all right, when current flows into the page, then there's magnetic field lines that wrap around in clockwise circles around that wire, which means there's a magnetic field line that wraps around like this, and where it meets the current in wire number 2, it represents magnetism that points downward. So this is the magnetic field created by the current in wire number 1, and then current number 2 responds to it. So use the right-hand rule, point your thumb out of the page, point your fingers downward in the direction of the magnetic field, and so with your fingers pointing down and your thumb pointing out of the page, you find that there's a force that points this way, meaning that these two wires are going to repel one another, okay? Wire number 1 is pushing wire number 2 to the right, and we could also argue in the same way that there's magnetic field lines that surround wire number 2. So if you point your thumb out of the page, then your fingers wrap around in counterclockwise circles. And so they wrap around, and where they meet wire number 1, there's some magnetic field pointing down. So that's the magnetic field from wire number 2, but there's a current flowing into the page in the vicinity of that magnetic field. So there's another right-hand rule in which you point your thumb into the page, you point your fingers downward, and then you see your palm is facing in this direction. So it just verifies what we found out just a moment ago, that if wire number 1 pushes wire number 2 to the right, we say they're repelling, and so that means wire number 2 should be pushing wire number 1 to the left. So this is a force of repulsion between the two wires. Now we just have to figure out mathematically what's the value of the force per unit length. So the force per unit length is equal to mu naught times I1 times I2 divided by 2 pi times the distance between the two wires. All right. And mu naught divided by 2 pi is just equal to 2 times 10 to the negative 7th. So we have a force per unit length equal to 2 times 10 to the negative 7th times 6 divided by the distance d, which was 60 centimeters or 0.6 meter. So 6 divided by 0.6 is 10. 2 times 10 gives us 20, and 20 times 6 gives 120. So we have 120 times 10 to the negative 7th force per unit length. I guess would have to be newtons per meter. We could probably say, all right, I'll move this decimal 2 places this way, and then I can change the powers of 10 here. So if we want, we can call it 1.2 times 10 to the negative 5th Newton per meter. You check and see if that's right. I left the units out, but this was Tesla meters per amp. That's amps, and that's meters. Okay.